Hello everyone, welcome to this brief overview of correlation and autocorrelation function. Let's start with correlation. So what is the correlation? Correlation is a relationship between two variables. You can see examples of two variables on the screen. For a positive correlation, two variables increase together or decrease together. For example, number of gallons of gas pumped is positively correlated to the amount spent on gas. Okay, so when you spend more on gas, the number of gallons of gas pumped will increase. As you see, both of them are increasing. Okay, another type of correlation is negative correlation. In this case, variables move in opposite direction. For example, miles traveled is negatively correlated to the amount of gas left in your tank. So when you travel more miles, that means increase in miles, will lead to a decrease in the amount of gas. Okay, so they move in the reverse direction and we call it as negatively correlated variables. One feature of correlation is of course direction. Let's take a look at the graphs on the screen. For example, a positive correlation occurs when both variables are increasing, but don't forget also decreasing at the same time. So both are increasing or both are decreasing at the same time. They are moving in the same direction. Our data set in this case will fall in an upward sloping direction. As you see the first graph on the screen, our data set will fall in an upward sloping direction when we have a positive correlation. So if we have a data set that points look like this, then there is positive correlation. As our variable x increases, here you see there's 0 and the values of x increases, y variable also increasing. Now let's take a look at a negative correlation. A negative correlation exists when our variables are going in opposite directions, meaning that as one variable is increasing, the other decreases. Let's take a look at point here. As you see, the y value is the highest, but x is the lowest. When you move down the line, you realize that at this point, y value is lowest when x is highest. As you see, when one is increasing, the other one is decreasing. In this case, our data set will fall in a downward sloping direction. So if we have a data set that looks like this, then we have negative correlation between x and y. If our data set does not seem to follow either one of these predictable patterns, like 1 and 2, no predictable patterns, then it may be described as having no correlation. No correlation means there is no discernible pattern that can be detected between the variables, meaning that no relationship exists. For example, in this graph here, the data set appears to be scattered, where it has no real pattern, so that we do not have any correlation between variable x and y. Correlation between the two variables are measured by correlation coefficient. Correlation coefficient takes values between -1 and 1 and is represented by letter R. Both the sign and the magnitude of correlation coefficient is important. A positive correlation is signified by a positive sign and both of our variables are going in the same direction. This indicates a correlation coefficient R between 0 and 1. A negative correlation means that our correlation coefficient R is from -1 to 0 or has a negative sign and our variables are going in opposite directions. No correlation R will be close to 0, so we'll have no sign and it means there's no relation between the variables. Another feature of correlation is its strength. The closer the number is to 1, regardless of the sign, be careful, regardless of the sign or the direction, the stronger the correlation is. We can get a basic idea of strength by simply looking at the correlation coefficient itself. As you see, the first one, the correlation coefficient is 1, which represents a perfect positive correlation. And our equal to plus or minus 0.8 or higher is typically referred to as a strong or high positive correlation. And our equal to plus or minus 0.5 to 0.8 is considered a medium correlation, while R of equal to plus or minus 0.4 or lower is usually referred to as a weak correlation or low positive correlation. Now we can have this for any types of correlation, positive or negative, that we are talking about before. For example, a strong positive correlation would fit a straight line. as you see here, or would be very close to that straight line. The closer the points in our data set are to that line, the stronger the relationship and the stronger our correlation, and the greater the number will be to 1. Let's say a weak positive correlation here in this case. Our data set still go in maybe an upward sloping direction. You can see here that our points are spread out more. They are not packed greatly around the line, so this would represent a weaker correlation. Overall, remember that correlation tells about the relationship between variables and how strong that relationship is and in what direction those variables are going. However, we cannot infer causality or say that one variable is impacting or affecting the other by just checking correlation. Next, I'm going to talk about autocorrelation. Autocorrelation is the correlation between values in the series and past values. So, what we do different than correlation here is that in correlation we have two separate variables. In autocorrelation, we are in fact checking, measuring the correlation between values in the series and the past values of the same series. Another way to think of autocorrelation is a correlation between pairs of values at a certain length. This means that we need to talk about a leg when we are discussing autocorrelation. For example, a leg 1 autocorrelation measures the correlation between immediate neighbors in the time series. So it's going to be a correlation between YT, the data you observe at period T, and the data that you observe at period T minus 1. Like you observe the data today, present value, and the data that you observed yesterday. So autocorrelation leg 1 measures this correlation. Leg 2 autocorrelation measures the correlation between pairs of values that are 2 periods apart. Say the data that you observed yesterday and the data that you will observe tomorrow. Let's look at autocorrelation through an example. Just a quick reminder, with proper software, we do not need to compute autocorrelations manually. For example, in Forecast X, we can get a table and bar chart displaying the autocorrelations for leg 0 all the way to the largest leg specified by the user. The plot of autocorrelation functions or the autocorrelation coefficients versus time lag is called Correlogram. As you see here, the horizontal axis is the time lag. So when it says 1 here, it's YT minus 1. And this data shows the correlation between YT and YT minus 1. The second bar shows the correlation between YT and YT minus 2. So you continue like that until leg 12. Here we see an example of correlogram that contains autocorrelations until leg 12. Let's see how we read this correlogram again. For example, the leg 1 autocorrelation is the correlation between the data at period T and the data at period T minus 1 and has a positive autocorrelation of 0.8. That means the data today and the data that yesterday I observed are highly correlated. Similarly, the leg 2 autocorrelation is the correlation between data at period T and the data at period T minus 2 and it is 0.5. We see multiple bars, like the first one and the second one, exceeds the threshold. So this is the upper limit as you see, exceeds the threshold. The thresholds are the horizontal lines and indicates that these autocorrelations are statistically significant. So if you see a bar above the threshold, you're going to say that this correlation between these two data is in fact significant and it is not zero. They are related. When we see bars are above the threshold, it's a good sign. It means that the series contains more information that we can model using one of our forecasting techniques. The autocorrelation plot can help us detect the data components and answer important questions in regards to the time series. The first question is, are the data random? So random means the data today you observe is not related to data you observed yesterday. Let's think about weather forecast. Yesterday was cloudy. In a random case, yesterday was cloudy and today it's totally different. It's not related what you observed yesterday. If the data is random, what do we expect? We expect autocorrelations between and for any leg are close to zero. The successive values of a time series are not related to each other because as you know, coefficient 0 means the variables are not related to each other. So you observe data randomly throughout the series. The second question, is there a trend? If the series has a trend and are highly correlated, then the autocorrelation coefficients are significantly different from 0 and will decline towards 0 slowly. A series that contains a trend is said to be non-stationary. So if there is a trend, the data you observe today is related to the data that you observed yesterday or 2 days ago. They are related. That's why their autocorrelation are in fact not zero. They are statistically significant. And finally, we can talk about seasonal pattern. If a series has a seasonal pattern, there will be a significant autocorrelation coefficient at the seasonal time lag or multiples of the seasonal lag. Look at this example. This is the Correlogram for mobile home shipment. Note that this data is quarterly. Using this figure, let's answer the questions. Are the data random? No. Why? Because check the coefficients, autocorrelation coefficients for until leg 12. All of them are above the threshold. That means all of them are statistically significant. That means there is a relation between the data you observed today and you observed the data yesterday, between the data you observed today and the data that you observed 2 days ago. I'm saying days, but you can just change the time period to quarter and years as well. And it continues until the 12th leg. So since all these autocorrelations are significant and high, we cannot say that data is random. It is in fact related to data that you observed in the past. The second question, is there a trend? Yes. As the autocorrelation coefficients do not fall below the critical level, which is an upper limit, at any leg, we can conclude that there is a trend in the data. If there is a trend in the data, it's not stationary. You might think the trend in the data is stickiness in the series. A positive spike at leg 1 is called stickiness. It means that high values follow high values and low values follow low values. If there is no autocorrelation or all autocorrelations are close to 0, that series is stationary. If the data is not related to the previous data and it's random, then it's called as stationary, and you cannot forecast the series, a stationary series, beyond a naive forecast model. So that completes the video. Thank you for listening.